Hey y'all, why is it so loud? Okay. I just got back from doing a whole lot of programming. So, I got I got the keys working. I have the stream, the both stream and HMI working. Keys and mouse input. So, key controls to all the digits, 0 to 9, the entire alphabet. Enter, shift, spacebar, and both controls, and the arrow keys, of course. And it has full mouse control, so it controls the mouse by change, so it doesn't control like the position. It only controls it by change, so it can go up, down. I can scroll vertically and horizontally, but I can't really show that right now. What else? Oh yeah, it can click, of course, and that stuff. So we can basically just start on the brain, unless I made some errors back then. The only thing that's really missing right now is audio and the spatial frequencies as another visual input. Keys, update keyboard. I don't think this needs to use update keyboard, right? I don't know. Okay, let's just get ready. Because this is where the actual brain comes in, finally. Even though we're typically still missing some parts, we can actually just start. So, figure out how I do this. On press key. Okay. So this is just this is how I quit. Listener background thread. Alright, so the AI goes here. And I guess we're gonna code from this brain, importing a bunch of stuff, I guess. Okay, let's get to it. I have a few games for the AI. Where is that thing? So I got Breakout here, and I got Pong. That's so the AI can play it. I'm not sure if I'm gonna get that far today, but I've already done a lot during my break. Alright. So we're still doing selective mapping here, which is basically just reinforcement learning. So stimulus to response. Hope I'm doing this right. Keys pressed, video features. Yeah, and it doesn't have direct access of the mouse location. It just sees it, and it's gonna have to recognize that that's the mouse. Okay, it gives the action corresponding to stimulus. So this is literally reinforcement learning. I guess I'm kind of hesitant because I like built up to this. So I can't really do it like this. Get rid of that. I can clear some of these. And I did a lot to get these keys working, like a ton of work. Yeah, I still have some ideas left over and stuff like that. Okay, I just want to check because my environment is my computer. Okay. And I need, oh, maze. Okay, give a reward. So, I'm not sure if this is supposed to, well, I'm not sure if this thing can run correctly individually. Because machine learning is able to run by itself. I guess we get the selective mapping and then we build onto it. So, with these other ones. Because I'm sure these other ones can't work on their own. Okay, let's see. This doesn't really look like a neural network. Oh yeah, and first time I'm gonna have to give it rewards manually. Because the way that this works. Hold up, for the reward system I might have to. Okay, hold on. I'm gonna just give it rewards manually. That might make it take extremely long. Yeah, because they normally take really long to teach. Hold on. I remember this was on a CNN from YouTube. CNN neural network coding. Yeah. This is what I use. This was really useful. Okay, here's the code. What happened to the code? Continue to destination. What the hell? Okay. Man, I did not know how to do this. I've seen this before, so. Log softmax. Oh, is that just a softmax function? Manual seed. So this is the part where I need to have a really good understanding. I can't just be copy and pasting around. Well, I can technically still do that, but I need a way better understanding to the point I can code this myself, because this is where my actual ideas come into play. Everything else was just general, and I figured it out along the way. Now this needs to follow the exact blueprints that I've given myself. Okay. Man. Okay, this is like an image one. How on earth do I do this? I guess this is all the inputs. So there's 44 binary inputs for the keyboard. I guess these have to be integers, because I think they go by pixels. You can't have like a decimal point. So these all go by integers. These three in the middle are binary, because those are buttons. And then the last ones are integers. Wait, what is an integer? I think I'm using that right. All delta values are positive or negative. Integers. Do I have anything in my files that's like just code? That'd be good if I already have something in here. Please. Oh, here we go. Alright, prototype matching, which is basically just this looks exactly like what the dude had. Pattern recognition unit. Okay. Gonna need to update that. And we're using torch instead of numpy. I don't want to be crossing over. It doesn't seem like it'll be useful. All right. Okay, this seems really simple though, shouldn't it? So we need an input, just all the inputs, give it an output. It needs to. I think I need to look at the original paper again. Okay, opened up over here for some reason. Ease of two. What the hell is that? I thought I removed that last time. Okay. Just make this a little easier for me. Okay. The actor selected mapping then determines. The response to a stimulus using a softmax policy. How? Oh yeah, I forgot what softmax was. Okay. Yeah, that makes sense. But what would the options be? Okay. Selective mapping is adjusted according to outcome values through standard reinforcement learning. Alright, I think this goes over like starting off when you have nothing as a task set, which is what the situation I'm in right now. A newer task that appears reliable. New one is created and part of this actor. This actor consists of new selective / predictive data and weighed according to contextual cues. Actor selective determinants. Okay. It needs to read all those inputs and generate an output. Hold up. External cues. would be changes in screen brightness and motion intensity. I think it's best to ask ChatGPT how the hell to do this. No? Okay. I think the question I asked was kind of bad. Alright, deep reinforcement learning looks good. I think I don't have a controlled environment because that was supposed to be based on emotions. Alright, I'm thinking back of some ideas. So I have this idea of a teacher type student where the teacher learns what you know what no, because that one we need to teach the teacher, and then that's just me basically teaching the AI manually again. I think one thing would be having a video representation, kind of like it watching me in all my inputs, playing the game for a little bit, and then thing will be playing for a little bit. No, I'll be playing for a little bit, and then it can try to mimic my actions. So, how I'm thinking I'm gonna do that is getting some kind of neural network and then forcing inputs through it and see if that works. Code walkthrough. This looks like what I need.
So since DQ learning is a little bit complicated to explain, I'm going to use the Fosenik reinforcement learning environment. It's a very simple environment. So I'm going to do a quick intro on how the environment works. We'll also quickly answer the question of why we need reinforcement learning on such a simple environment. Next, to navigate the environment, we need to use the epsilon greedy algorithm. Both Q-learning and DQ learning uses the same algorithm. After we know how to navigate the environment, we're going to take a look at the differences of the output between Q-learning and DQ learning. In Q-learning, we're training a Q table. In DQ learning, we're training a DQ network. We'll work through how the Q table is trained, then we can see how it is different from training a DQ network. In training a DQ network, we also need a technique called experience replay. And after we have an idea of how DQ learning works, I'm going to walk through the code and also run it and demo it. Just in case you're not familiar with how this environment works, quick recap. So the goal is to get the learning agent to figure out how to get to the goal on the bottom right. The actions that the agent can take is left. Internally, we're going to represent that as 0, down is 1, right is 2, up is 3. In this case, if the agent tries to go left or up, it's just go.
So, what I'm planning to do here, let me fix that. So, I'm going to first let this video play, and I'm going to, and when he tells me to code, I'll code exactly what this is, and then I'll try to find a way to try to force through, or make it watch something, and realize how to do that through it. And then it'll use what's watched as positive input. I don't know. I mean, humans, because I have to base this off of humans. Humans get inputs and outputs. No, positive and negative, like neural signals, neurotransmitters. Yeah. So I think my best way is just manually giving it positive or negative input, positive or negative confirmation. And the problem is it understands that way too slow. So that's what the issue is.
Going to stay in place. So in general, if it tries to go off the grid, it's going to stay in the same spot. Internally, we're going to represent each state as this one is 0, this one is 1, 2, 3, 4, 5, 6, all the way to 14, 15. So 16 states total. Each attempt at navigating the map is considered one episode. The episode ends if the agent falls into one of these holes or it reaches the goal. When it reaches the goal, it will receive a reward of 1. All other states have no reward or penalty. Okay, so that's how this environment works. At this point, you might be wondering why we would need reinforcement learning to solve such a simple map. Why not just use a pathfinding algorithm?
I'll need to watch that.
In terms of how the agent navigates the map, both deep Q learning and Q learning uses the epsilon greedy algorithm. Basically, we start with a variable called epsilon equal and set it equal to 1. And then we generate a random number. If the random number is less than epsilon, we pick a random action. Otherwise, we pick the best action that we know of at the moment. And at the end of each episode, we'll decrease epsilon by a little bit at a time. So essentially, we start off with 100% random exploration, and then eventually near the end of training, we're gonna be always selecting the best action to take. Before we jump into the details of how the training works between Q-learning versus deep Q-learning, let's take a look at what the outcome looks like. For Q-learning, the output of the training is a Q table, which is nothing more than a two-dimensional array consisting of 16 states by 4 actions. After training, the whole table is going to be filled with Q values. For example, it might look something like this. So in this case, the agent is at state 0. We look at the table and see what the maximum value is. In this case, it's to go right. So this is the prescribed action. Over at 0 value for actions. After training, the whole table is going to be filled with Q values. For example, it might look something like this.
Okay, so you might.
So in this case, the agent is at state 0. We look at the table and see what the maximum value is. In this case, it's to go right. So this is the prescribed action. Over at Deep Q Learning, the output is a Deep Q network, which is actually nothing more than a regular feed-forward neural network. This is actually what it looks like, but I think we should switch back to the simplified view. The input layer is going to have 16 nodes. The output layer is going to have 4 nodes.
Yeah, this is the part that I need. Well, this is the part that I need, but I guess I need because I want to understand how this is what I need.
The way that we send an input into the input layer is like this. If the agent is at state 0, we're going to set the first node to 1 and everything else 0. If the agent is at state 1, then the first node is 0 and the second node is 1 and everything else is 0. So this is called one-hot encoding. Just do one more if it's at the last. If we want to put in state 15, then everything are zeros and state 15 is 1. So that's how the input works. With the input, the output that gets calculated are Q values. Now the Q values are not going to look like what's in the Q table, but it might be something similar. Let me throw some numbers in here. Okay, so same thing for this particular input. The best action is the highest Q value. When training a neural network, essentially we're trying to train the weights associated with each one of these lines in the neural network and the bias for all the hidden layers. Now, how do we know how many hidden layers we need? In this case, 1 layer was enough, but you can certainly add more if necessary. And how many nodes do we need in the hidden layer? I tried 16 and it's able to solve the map, so I'm sticking with that, but you can certainly increase or decrease this number to see what happens. Okay, so that's the differences between the output of Q-learning versus deep Q-learning. As the agent navigates the map, it is using the Q-learning formula to calculate the Q values and update the Q table. Now the formula might look a little bit scary, but it's actually not that bad. Let's work through some examples. Let's say our agent is in...
Alright. So I'm going to try to apply this to what I have. So I just thought up of it. I have 44, let's see this. Yeah, 44 of these and then 6 of those. So that's 50 actions in total that I can control. Some of them are binary. Actually, only 4 of them are not binary. Maybe I'll have to put that in a different section. I don't know. How would non-binary values even work? I'll have to think about that later. Now, this is the problem here. Number of states. There, it's the entire screen. There's not really a number of states. Unless you count a certain image for each. In that case, it's near infinity. Yeah, basically infinity. So, how am I going to make this Q table? This is the same problem that any kind of high resolution thing would have. So, I don't know.
15. We're calculating Q of state 14, action 2, which is this cell. The current value of that cell is 0 because we initialized the whole Q table to 0 at the beginning, plus the learning rate. The learning rate is a hyperparameter that we can set. As an example, I'll just put in 0.01 times the reward. We get a reward of 1 because we reached the goal, plus the discount factor, another parameter that we set. I'll just use 0.9 times the max Q value of the new state. So the max Q value of state 15. Since state 15 is a terminal state, it will never get anything other than zeros in this table. Max is 0. Essentially, these two are gone. Subtracted by the same thing that we had here. Okay, so work through the math.
Like what on earth? Okay.
This is just 0.01. So we get 0.01 here. Now let's do another one really quickly. Agent is here, take a right. Q of 13.
I can use this because the
Going to
concept
the
of a
right.
Q table
13 is
not
also
applicable to
all
our
zeros. Over at Deep Q Learning, the formula is going to look like this. We set Q equal to the reward if the new state is a terminal state.
Hey.
Hello everyone. In this video, you'll learn all about reinforcement learning, how to train ChatGPT, and build the world's best Go playing program. But let's start with something simpler. Remember Pong? It was one of the very first video games. The player on the left has a simple policy. It just follows the ball up and down. Let's train an AI Pong playing agent to compete with it. To do this, we'll need to define a policy that takes the state of the world as input and outputs an action, up in this case. As input, we'll take the ball X and Y positions and the two paddle positions. We'll also include the velocities, so our policy will get 8 inputs. To keep the figure simple, I won't show the velocities. We'll represent our policy as a neural network. Our network will multiply each of these values with a weight and sum them up. Network will multiply each of these values. We'll represent our policy as a neural network. Our network will multiply each of these values with a weight and sum them up. We'll add a sigmoid function to convert the result to a value between 0 and 1. If the result is larger than 0.5, we'll
Right.
the neural network. Our network will multiply each of these values with a weight.
Okay. with a weight. So I'm gonna just be making this along the way. I really hope it didn't skip like that, but whatever. Okay. So it's given a crap ton of inputs. What even is my resolution? Here we go. And then 3 channels. And then that another time. Except the other thing has basically 1 channel. I'm not going to include all those other ones. See, this actually makes a lot more sense. Goodness, man. So we need all the dimensions in there first. So
and sum them up.
I'm gonna just keep watching.
We'll add a sigmoid function to convert the result to a value between 0 and 1. If the result is larger than 0.5, we'll move up, otherwise down. That's it. Great, let's play some Pong. We'll start with random weights. Our random Pong player isn't very good. It just hides in the corner. This is like if you've never played tennis and you're matched against Serena Williams. You'd probably hide too. Or maybe you'd ask your opponent how to play. Suppose your partner told you exactly what to do for every step. We can use this kind of supervision to train our policy. Let's say our coach says to follow the ball. Here the ball is above our paddle, so the right answer is up. But suppose our network outputs 0.2, which means down. We'd like to change that 0.2 to a 1.0. Here's a different case where the right answer is down, and we'd like to drive the output to 0, a more confident down answer. We can accomplish this by defining an error function and optimizing the weights to reduce this error. Instead of numbers, let's draw these weights as colored lines. Positive weights are blue, and negative weights are red.
Man, how do I even... Alright, I just need to start off with the inputs. Let me look at classes, because that's how they do it, right? Why is it typing like that? Width, height, channels. Just turn this into width 1, height 1, channels 1. And then this is for what should be the same thing. I'm getting an image eye check in there. Self. What does this even mean? Channel 1. So that's the width, height, and channels 3. And put definition inputs. It's just going to be given a matrix. Screen matrix, MHI matrix. Keys and mouse.
Hey Nick, what you been working
Last
on?
time I watched this dude's video, I learned like nothing from it.
In the description below. So you'll be able to pick up, save our model as well as where to log out. Then with import. Now, on to
I don't want to import gem. Okay. How am I supposed to do this? Manual input.
Optimization step. If we train on thousands of actions, the weights on the right start to converge. Now that we're trained up, let's play some games. Our Pong playing agent is pretty decent now, although it doesn't win very often. How can we train our agent to win more? Well, you can think of the game as a sequence of actions, which may lead to a loss or a win. Suppose we lose. We'd like our coach to tell us which actions were at fault. Maybe we messed up at the end. Then we could retrain our policy based on this feedback, as we've been doing before. Training a network like this is called supervised learning, and you need access to a really good coach. But suppose you don't have a coach. All you know is that this sequence of actions resulted in a loss, and this one produced a win. This kind of problem is called reinforcement learning. We don't know which actions were responsible, so we'll just penalize all actions we made in the loss, and reward or reinforce all actions we made in the win. This converts it into a supervised learning problem, just like we solved in the first part of this video. Actually, we can do a little bit better by penalizing later actions more, as the game losing the stake typically happens towards the end, and similarly for rewards. After training on 3,000 games, our agent has improved to play about as well as the opponent. You can see the score is pretty even.
See, like, I don't have time for this. It's just the training that's the issue. It needs to be like super smart.
And after about 12,000 games, our agent figured out that hitting the ball with the corner of the paddle makes it go faster. Cool.
It really shouldn't take that many games, though.
4 values, and you're just
I'm gonna just
effectively
try doing stuff because that's the.
we're going to have binary
The
flags,
best
so
way.
ones or zeros represented in those positions. So it's a one hot encoded vector of different actions or different spaces. You've also got multi-discrete, so this is very similar to our discrete space, but in this case you can have multiple sets of values. So you'll types of spaces. These are ones that I haven't dealt with too much, but it's important to note that they're there. So you've got a multi-binary space. So this is a one hot encoded set of binary values. So if you pass through multi-binary and pass through the value 4, what you're going to get is a list of values, and you're going to have 4 gym to instantiate our environment, and then we'll actually test it out and take a look at it. So let's first up load our environment. Okay, that is.
I might as well make this a Jupyter thing. I'm gonna just save the brain as what it is right now. Man, this is difficult. I haven't done anything yet. I have to do something. You know, it can't be this. 'Cause I don't know what that is. I guess I had high expectations. This is a lot of shit. How do I search? I'll just make a new one. Okay. Dude. Okay. I don't want to be trying to write down notes and not actually understand what I'm looking at. I think that's the problem I ran into a lot of times. It was like 90% writing and only a little bit understanding.
Is 2 lines of code to be able to go and create our environment. Now, I've gone and separated it out into 2 lines of code, but you can make it one, and I'll sort of explain this.
Let me make sure it isn't using it. Yeah. That isn't using a G.
Or -V0. Now, this is case sensitive, so make sure you get the case correct. So we've got a capital CART, PO, actually particularly our reinforcement learning, but so much easier, trust me on this, before you try to do anything, because you might be trying the wrong algorithms, you might be doing a whole bunch of random stuff, but understanding the environment is going to make your life so much easier, trust me on this. So let's go on ahead and write a bit of a loop to test out our environment. So let's go do this. Alrighty, so I've written a lot of code there, but I'm going to take it step by step with you. So again, we're going to take this step by step whenever we're going through this stuff. So what is that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 lines of code. Now again, all of this code, including the beginner as well as the completed tutorials, are going to be available in the GitHub description below. So if you want to take this and walk through it and compare your code, you can do that. First up, what we're going to do is walk through each step or each line of this code. So what we're actually going to be doing is we're going to be trying to test out the cart poll environment 5 times. Now, what we've actually gone and done is created a variable called episodes, and we've set that to 5. So this means that we're going to try to loop through our environment 5 times to see how we can operate within it. So we've written episodes equals 5, and then we're looping through each one of those episodes. So for episode in range, and then we're starting off at 1, and then we're going episode plus 1. So this is effectively just looping through each one of the episodes. If we actually wrote this out, so episodes equals 5 for episode in range 1, comma, episodes plus 1. Let's print out our episode. So you can see that it's just going to be looping through 1 to 5, right? So that's all these 2 lines are doing here. Then what we're doing is we're resetting our environment. So by running env.reset, we're going to get our initial set of observations. Remember, there was those 5 key components to any environment, or 4 key components. There was the agent, the action, the environment, and then the observations plus the rewards. So by running env.reset, we're going to get our initial set of observations. So if I type in env.reset, you can see that these are the observations for our particular environment. Now, I'll talk about what these values mean in a second once we actually get to understanding the environment. But for now, just understand that these are the observations that we get for our particular poll, right? So we're getting these 4 values. Now, what we're effectively going to be doing is passing these observations, or later on, we'll pass these observations to our reinforcement learning agent to determine what the best type of action is to be able to maximize our reward. So our agent's going to see these values and it's going to go, hey, I've got these values. What should I do, or what action should I take to be able to maximize my reward and get that bar in the straightest possible position? Then over here, we're just setting up some temporary variables. So we're setting whether or not the episode is done. So you've got a maximum number of steps within this particular environment. And we're also setting up a running score counter across the episodes. Then we've got a while loop. So while not done, we're then going to render our environment. So the render function allows us to view the environment, or view the graphical representation of that environment. Key thing to call out is if you're running this inside a Colab, the render function is not going to work like this. You got to do a little bit of extra work. So hit me up in the comments below if you want a little bit of help with that. Then what we're doing is we're generating a random action. So rather than taking in our observations and actually generating an action which is actually useful, we're just going to take a random one. So this is akin to doing this. So I can just type in, let's actually move this down. So what we'd be doing is env.actionspace.sample. So we're just generating a random action. This is actually really good to note as well. So if I actually take off sample, remember how I was talking about the different types of action spaces? In this case here, we've got discrete is 2. So this will mean that we get 2 different types of actions. So we've got 0 or 1. So if we actually type in .sample, you can see we've got 1 this time, got 1, got 1, got 0. So you can see our action space is just going to have those 2 different actions, 0 or 1. This is what discrete 2, which is what our action space looks like, represents. Now we can actually take a look at our observation space as well. This is a key thing to call out. So there's going to be 2 different spaces within any environment. Your action space, so these are the actions you can take on that environment, and your observation space. So this is what your observations actually look like for that particular environment. So it's a partial view. So if we type in observation space, you can see that we've actually got a box environment. So we've got these values here. So that's going to be our lower bound, and this is going to be our upper bound. And then we've got 4 comma. So this means that we're going to have 4 values. So 0, 1, 2, 1, 2, 3, 4. And then they're going to be in the D-type float 32. So again, you can start to see how our environment is actually built up. Now again, we can sample this if we wanted to. And this is going to look almost identical to what we get from env.reset up here. Then what we can actually do is we can actually pass through our random action. So this is the next line that we've written. to our environment. So we can do this using env.step. So if we actually did that, so env step and pass through the values 1, you can
Okay. Oh, no errors. Man, I'm getting tired and I don't know what I'm doing. I don't think I've learned much here. What is this? Yeah, don't look at that. Oh. I mean, I think I've got myself in the right place. Definitely. I think the learning from here is just going to be really slow, the development. But this does look like something good. I don't know what I should do. I guess I should just go to sleep. Kinda didn't do much this video, but it is what it is.